Hello everyone, I'm going to walk you through these force diagrams and show you why each diagram goes with each scenario. So here we have a skydiver accelerating towards the ground. There's nothing underneath him, so there's no normal force, which is your support force. But since you're on Earth, you have this gravitational force or force of weight. Those are the same thing. So if ever you see FW or FG, they are the same thing. Now he is going pretty fast, so there's going to be some air resistance, and we call this drag. And it says here that he is accelerating towards the ground, so he's speeding up going downwards. So this force is going to be stronger because it's pulling him down faster. All right, here we've got a guy that is pedaling up a hill. So again, we have force of gravity. Gravity always goes straight down. It never goes at an angle. If it did go at an angle, we would just be sitting here one day and then all fly to the wall. And that's not happening here. So gravity is always going straight downward. Normal force will always go perpendicular. Perpendicular is at 90 degrees to the ground. So here's the ground like this. So normal force should go like this, and we see that here. Now he's pedaling uphill, so there is an applied force, and it's going up the hill. And then we have friction force because the tires are touching the ground. Now on your sheet, it says like the direction of net force. That just means which direction is the stronger force pulling. So here it says slowing down while riding a bike up a steep hill. So it seems like the stronger force will be going downhill because it's forcing him to slow down. So that's what you would put there. If you need any extra help on net force, let your teacher know and we'll help you out with that. Okay, here we have a boat at rest in the water. This is the only time that we actually use a buoyancy force. Buoyancy is basically like a float force. You can read your definition. It'll give you some extra information with that. But just know that it's basically like a floating force. And then you're on Earth here, so you'll have your gravitational force as well, or weight force. Since the boat is at rest in the water, these arrows are going to be the same length. Okay, here, same thing, except you have a book sitting on a table. So you'll have your gravitational force, but instead of a buoyancy force, you'll have your normal force because you have that normal supporting force, which is coming from the table. So both of these arrows will be the same length. Okay, here we have this guy that is pulling a box by a rope. Okay, so we are really looking at the box itself with the rope, not necessarily looking at the guy. So here we have tension force that is pulling the box to the right. He's on Earth, so you have normal force and gravitational force. And because he is touching the floor, or the box is touching the floor and it's moving, you'll have that friction as well. Now, all of these arrows are going to be the same length because it says constant velocity. And so if it's not speeding up or slowing down or starting to move or coming to a stop, it's all going to be a balance force. All right, here we have the guy pushing a rock up a hill. And we see that you have gravity here. Normal force will be going at a right angle. And since he is pushing the rock up the hill, you'll have the applied force going up the hill. Rock is touching the ground, so you'll have this frictional force. Now, this is a stronger force here because it is causing it to accelerate or speed up going up the hill. Okay, here we're just looking at the barbell hill here. So it's not touching the ground, so you're not going to have normal force here. So, but you are on Earth, so you'll have gravity, and you'll have the pull of the guy, so pulling from a living person. You'll have the applied force. Now, this force is stronger than this one because it's speeding upward. All right, here we've got the guy that's water skiing. So here we've got gravity again. We have drag because he is going pretty fast through the air, and you'll have tension force coming from the rope. Now, the reason why this is normal force instead of buoyancy force is because he's actually going so fast across the water. He's not floating. He is just hitting the water so hard that it's actually acting like concrete. And so that turns it into a normal force. Now, if it was buoyancy force, he would actually sink in the water and start floating, but that's not the case here. All right, here we've got a backpack hanging motionless by a shoulder strap, the strap or a rope. That's going to be a tension force. Again, you're on Earth, so we have gravity here. And it's hanging motionless, so it's not moving, so these arrows will be the same length. All right, here we've got another tension force here, but he's balancing on a tightrope. Now, the tightrope is going up at an angle, and we see that here. And then we've got the gravitational force here on Earth. No normal force because it is through a rope. Okay, a car coasting to the right and slowing down. So the car coasting means you're not hitting the gas or the accelerator. So you have no applied force here. Instead, you're just going to let the car slow down on its own. Well, because the car is touching the earth or the touching the road, you'll have that friction force. And then again, you have normal force and weight. So friction force is only acting on this going to the left. All right, here we have an apple that is free falling from a tree. It's not going super fast, so you will not have any kind of air resistance, but you will have gravity. Here we have an airplane flying through the air at a constant speed. So you have drag because of the air resistance and the applied force because of the engine pushing it forward. You have gravity, and then lift is what's actually causing it to stay in the air. All right, here we have a barrel accelerating upward by being pulled by a rope. So we're just looking at the barrel here. So you have tension force and weight, and that tension force is stronger because it is accelerating upward. Here we have a car speeding up. You have normal force, and I'll be done in just a minute. Just put it right there. Okay, we're on Earth, so we have gravitational force and normal force, friction because he is moving forward, and then the acceleration of the car's engine will be our applied force, and this one's stronger because it's speeding up. And then last we have this little dude sledding down a hill. So we have gravity, you have normal force going at a right angle to the ground, and because he's on an icy hill, there's going to be a little bit of friction, just a little bit. There's no applied force because he is not actually pushing himself down the hill. All right, y'all, hope this helps you out.